Good morning, everyone. It's my pleasure to present our work data-driven set-based estimation using matrix zonotopes with set containment guarantees. Dealing with cyber-physical systems comes with its drawbacks. For example, there are many accidents in using Tesla and Uber self-driving cars in the recent years. And also, dealing with industrial robot is a threat to human life. And from real life to simulation, we have this robot aims to go to the green circle. However, during simulation, it goes to unsafe situation and hits the wall. And the question that we are asking, how to guarantee safety when dealing with cyber physical systems. We propose using set-based estimation and having safety guarantees. The big picture behind the safety guarantees in set-based estimation can be summarized in this slide, where we have a car, and these are the trajectories of the car. And we have a pedestrian, and we aim to guarantee the safety of the pedestrian. We start from the initial set, which is the initial position of the car, and we compute a set that contains all possible trajectories of the car. This set is called the reachable set, given some measurement about the car, and then we check the intersection with the unsafe set. If there is no intersection with the unsafe set, we say that we guarantee safety. State can be position, speed, acceleration, and so on. And set-based estimation estimates the set of reachable states from its name of a dynamical systems given some measurements. For example, the reachable set R of n is an example of the reachable set at time step n. However, set-based estimation traditionally requires a model F bar that takes the state x of k, the input u of k, through a model plus some noise to the new state x of k plus 1. Cyber-physical systems, however, are becoming too complex to model. One often has a lot of data but no model to guarantee safety. We have done experiments to show the danger of depending on a single model in the cyber-physical systems. For example, we have this SIVA car aims to park autonomously on the yellow parking lot, and on the left-hand side we have untuned model, and on the right-hand side we have tuned model. As you can see, for the untuned model, it goes to unsafe situation and hits one of the standing cars. And for the tuned model, it will park safely. So it's really critical to choose a model, and might be dangerous to choose and trust a single model. Instead, we ask, can we depend on data without trusting a single model? This leads to ask a question how to compute over-approximate reachable sets from data. We have black box embedded system. We have the input to the black box embedded system, and we have the output. And we aim from the input and the output to compute the reachable set and check the intersection with the unsafe set. If there is no intersection, we say that we guarantee safety. The big picture behind our proposed data-driven set-based estimator is as follows. We have an offline phase where we collect input-output data, from which we compute a set of models that's consistent and can generate this input-output data. The set of models contains for sure the true model. Then we use the set of models into the time update, where we propagate the old reachable set to the new reachable set. And then we do the intersection between the time update set and the measurement set into the measurement update step, and so on. I have divided the remaining part of the talk into the following. I will talk about basic reachability, and then how to compute time update set, and then how to compute measurement update set. So let's start. As I am dealing with sets, I need set representation. For this, I am using Zonotopes, which consist of a center and list of generator vectors. For example, a center and one generator construct a line. If we add a second generator, we will construct this shape and we will have a center and two generators as a zonotope. If we add a horizontal as a generator, we will end up with this shape, which is a zonotope with 3 generators. We can construct complex shapes using zonotopes. Also, we have a matrix zonotope, which consists of a center matrix instead of vector for the center and list of generator matrices as a set representation instead of the generator vectors in the zonotope. Zonotopes have nice properties that you can do complex operations on sets using simple computations. For example, linear map can be computed easily by multiplying the center by L and the generator by L. The Minkowski sum, which means adding each point from the first zonotope to each point to the second zonotope, can be computed easily by adding the centers and combining the generators. Cartesian product, which means the vertical alignment of all the points from the first zonotope to all the points to the second zonotope, can be computed easily by vertically align the centers and having the generators as shown here. This nice properties qualifies the zonotopes to have an easy model-based time update. So if we assume that we know the model, we assume linear model for this paper, which is A bar, B bar, and we have the linear model x of k equal ax plus bu plus w. For the time update, if we know the model, it will be easily A bar multiplied by the reachable set, which is a linear map, and instead of multiplication between the A bar and the state. And instead of summation, we will have the Minkowski sum between sets. And instead of the noise, we will have a set that bound the noise. We assume the noise is bounded, but we don't assume a distribution for the noise. Or it can be written as A bar, B bar multiplied by the Cartesian product between the reachable set and the input zonotope Minkowski sum ZW. There are different techniques using set-based estimation, using ellipsoidal techniques, zonotopes, constrained zonotope, active learning. However, in our approach, we don't assume a model, and we depend on noisy data, and we compute a robust set which over-approximate all the possible trajectories of the system. For the time update set, let's see how to compute a time update reachable set. The proposed approach, as I have summarized before, is as follows. We have a noisy data, and given the noisy data, there is no single model that can be trusted and fits the data. Instead, we compute a set of models that's consistent with the data instead of depending on a single model. And we guarantee that the true model is inside the set of models. And then we propagate ahead using the set of models starting from the initial set given some intermediate measurement. Let's define the set of models. We assume the A bar, B bar are unknown, but we assume the C, which is the output matrix, as known. And we have the input from U0 to UT-1, which is the trajectory length, the output, and let's denote the state data as X and X plus, which we don't have access to. We have set of models, which called N sigma, and the true model is inside the N sigma for sure. And the set of models is defined as all the A's and B's that satisfy the data and the system model and the noise bounds. Let's compute an over-approximation for the set of models. The idea is as follows. We have a bounded matrix, matrix zonotope for the noise matrices, and we move along the noise zonotope and we compute a corresponding set that's considered a over-approximation for the set of models. Let's see how we do that. We have x plus equal AB xu plus w from data and the system model. We don't know the AB, so let's have it on one side, and we don't know the W. So let's have it as a single point inside the matrix Zonotope with a specific beta. And then let's move along the MW. This will result to M sigma, which is x plus Minkowski sum MW multiplied by the pseudo inverse of the data, which will contain all the models on in sigma, and consider over approximation for the set of models. Next, let's compute the set of models using input-output data. Until now, we have learned how to compute the set of models using the state data, which is x plus and x. However, we don't have access to x plus and x. Instead, we have access to the output, which is z plus and z. The idea that we determine the mapping of the observation z plus and z to the corresponding state space region. This can be done by computing a matrix Zonotope that contains all possible z plus and z given x plus and x. So we will have M sigma equal a matrix Zonotope that contains all possible x plus given z plus and Minkowski sum MW, and a matrix Zonotope x given z, which contains all possible x given z. Then, instead of propagating ahead using single model in the model-based case, we will propagate ahead using the set of models M sigma, and we have a specific input here. Next, let's compute the measurement update step. So we have the time update reachable set, and we do the intersection with the measurement set using two different approaches to compute the reachable set after the measurement update step. The first one depends on reverse mapping, where we determine the mapping of the measurement to the corresponding state space region as we have done before. So we take the SVD of the output matrix, and then we compute a Zonotope x given y that contains all possible x given y and the noise bound. And then we intersect with the time update reachable set, given that we have computed the Zonotope x, we have computed the Zonotope x given y, we intersect with the reachable set. The second approach is intersection, where we intersect the time update reachable set and the regions that correspond to the y with noise. And then we over approximate the result by a Zonotope RK. The output of the proof is shown here. And for details, we refer the listener to the paper. As an example, we have the model as a rotating target A bar, B bar, and we don't know the model. And we have three sensors with different output metrics, and we have different output noise Zonotope. And this is the reachable sets that over approximate the true x of k, which is in dash x, using the two approaches, the intersection approach and the reverse mapping. On the left-hand side, we have it using Zonotopes, and on the right-hand side, we have done also constrained Zonotopes, where we have the two approaches aligned as the result is exact. This is a snapshot with the approach, reverse mapping, and the intersection using constrained Zonotopes and using Zonotopes. And we have compared against the Kalman filter with 3 sigma bound, where we compute the ellipsoid with 3 sigma bound, and the x and the plus here is the true x of k. I acknowledge my co-authors. This is my website and the GitHub for my code. Thank you very much.